Hi everybody, welcome back to the second part of this mini-series about sorting algorithms. As you can see, we are back on the GitHub repository. Last episode, the first episode so to speak, was about the linear sort algorithm. And this time we take a look at the bubble sort, which is kind of fun sorting algorithm. I really like it. It's a bit bubbly, but I don't know. I have no idea who came up with this idea. I feel like it's quite nonsensical. It's just so redundant in my opinion, but it's still quite a fun time. So let's basically jump right into. Oh, by the way, if you didn't watch the previous video, you can find all these or this repository, all these algorithms at github.com/christopherclicks/sorting_algorithms. You can see the URL on my screen right here. It's free to use. It's under the MIT license, so do whatever you want with it. If you have some ideas, if you there are many sorting algorithms that are not that known. If you want to contribute and you have a sorting algorithms, just take a look at how I structured these sorting algorithms, and then you can kind of make your own version of it and just send a pull request, and I'd love to merge it into the current project. Enough for now. Let's jump right into VS Code. Let me, for performance reasons, quit the video right here, so we have a smooth screen recording. Yeah, we are back in our main sorting script. In this case, it's bubblesort.py. If you're unfamiliar with the structure, you have the bubblesort folder, the directory where we have technically. Well, we have this py cache, which you can ignore, and we have the three files, bubbles_sort.py, readme.md, and until.py, util.py, sorry. And readme is just text where you can see it's still to do. I have to do this one. But there should be, when you're watching this and downloading this, there should be some instructions in there. Util.py is just some utilities that you don't need to bother about. Is just generating a random list and stuff like that. It doesn't really have to do anything with the main sorting algorithm. And as you might have guessed, the main sorting algorithm is in bubble_sort.py. And this is the file that we have opened right now. So let me close the sidebar so we have a nicer screen right here. And as you can see, we are importing everything from the util module, the generate list function, print line function, and get timestamp function. In this case, I also have from the time module the sleep function, which we don't use. I just implemented this one as part of the debugging mode, so you can kind of slow down the sorting algorithm and see step by step how this algorithm works. For now, we don't have to care about this. It's not implemented right now, so it's just the sorting algorithm as fast as possible. As you can see, we have two functions, the sort function and the main function. And we only call the main function, which is just general practice. You don't need technically to have a main function, but I like to kind of keep it kind of organized and do it similar to like, for example, C, where you have the int main function, where you just have a main function that is called. It kind of lets everyone who's reading the code know, okay, well, this is the part that is getting called. Now let's take a look at this one for now. And as you can see, there's a lot of print stuff. So this is just simply printing instructions and stuff like that. But before we go through the code, let me show you the algorithm. So let's go back and go into our bubbly sorting algorithm. There we go. And let's run bubblesorts.py. There we go. So as you can see, the only thing that is happening is there we go, printing some ASCII in the terminal, some instruction, welcome to sorting, and we are getting asked for an input. What is the length of the unsorted list? So let's just say 10, and we get an unsorted list. That is very great, but we want to sort. So press enter to start sorting. I press enter, and there we go. We have a sorted list now, and it took roughly 0.107 seconds. Now, quick disclaimer before we get started with the actual sorting algorithm. The timestamp right here doesn't really represent the actual processing time when it comes to small list sizes. Again, I said that in the previous video. Python is a very abstract language. It uses, you just write the script, and Python is the interpreter who is then running the script as efficient as possible, but it's still quite slow. So you won't see a real difference between different sorting algorithms with lists of size 10, 20, 30, 1,000, 10,000. The only real difference where you start to see a difference is probably in the range from 10,000 to 100,000. And I said that in the previous videos as well. When I run a sorting algorithm with a size of 100,000, linear sort takes roughly, I think it was like 556 seconds, where merge sort takes 2.6 seconds. And let's take a look at how bubble sort performs here. So let's go with 100,000. This is 100,000 right here. And this is our unsorted list. And as you can see, it's a lot of numbers right here. And let's press enter, and now the algorithm is sorting. So it's not crashing. It's like this blinking prompt just says calculating and waiting for this response. And I actually have no idea how long this will take, but I will just talk for a couple of seconds to see if we can get this done. But my guess is that it will take several seconds, if you understand how the sorting algorithm works. And we will take a look at this in a second. But just to give you an idea, we have been waiting now for a couple of seconds, like easily above 10 seconds. Let me abort this right now. Let's go back and cd into our merge sort and just run our merge sort algorithm with again a list of 100,000. And let's press enter. And as you can see, it only takes merge sort 3.8 seconds to sort a list of size 100,000. So it's so much quicker than the bubble sort and linear sort, even though we don't even run bubble sort to the end. And I can promise you it takes several minutes for bubble sort to bubble everything through and sort it. The same for linear sort. Linear sort takes several minutes to actually get it done. But merge sort always gets it done in like a couple of seconds. So no, wait, yeah, that's correct. Let me go to bubble again. There we go. And run bubble. Well, okay, there we go. So again, if we take it with a short list of 10, it doesn't really make a difference. So let's take a look at how bubble sorting actually works. What is the concept? What is the main idea? And where does the name bubble come from? So just to give you a quick overview, the only thing that is happening here is right here on line 52, where we create a variable called sorted list, which is empty. And you can see it's a list. And we call the function sort and pass in the unsorted list that is generated above. So it's just a random generated unsorted list. We pass it into the sort function, and the result, the return value of sort, is then stored in the sorted list. So let's take a look at the function sort. So you can see we take one argument, one input, which is unsorted list. Now, if I expand this, you can see, well, that is actually very, not a lot of code. And you're right, it's actually very simple. It's just a repetition that is taking place a couple of times. And as you can see, we do have a while loop, we do have a nested for loop, and we have a couple of if statements, which already seems kind of redundant, and it is, but let's go through it step by step. So when the function is called, the first thing that is happening is a variable called isSorted is initialized and set to false, which kind of makes sense because we just started the sorting algorithm, so it definitely is not, like, probably is not sorted. So we set it to false. And then we have the main block right here, which is our while loop. You can see the sleep function is commented out, so this gray stuff right here isn't working. So we can say this is actually just, this is just the while loop. And this is repeating while it is not sorted, which is curious, and we will get to this in a second. And so as it seems like, the while loop will stop when it is sorted. And then we just, again, you can skip this, but I thought it would be for beginners easier to understand, and it looks nicer. It's not efficient, but it looks nicer. We create a sorted list variable, and we store the unsorted list in here. Okay, that is interesting. And then we return the sorted list. So what this line means, okay, when we break out of this while loop, and we break out if is sorted is true, so that means something is sorted, and that means that apparently the unsorted list is equal to a sorted list. So we take the unsorted list and we store it in sorted list, which means that I think that it should be now sorted, and then we return the sorted list. So the main part is happening right here. But what is happening? Well, this syntax right here might not look familiar to you if you come from C or JavaScript or something. But what that simply means is in JavaScript, or rather in C, for example, you just say while is sorted not. So bang is sorted, exclamation point or exclamation mark is called bang is sorted, which is simply meaning the opposite. In Python, you just say while not is sorted. So if is sorted is false, and while it is not true, so false, it will repeat, if that makes sense. So it will repeat until is sorted is not false anymore, but true. Then it will break out, or just continue with the script, the program. The first thing that in each iteration happens is changes made underscore made, or just changes made, is 0. So we create a variable called changes made, and you can see its type is an integer, and we store 0 in it. Great. But what happens next? So we have a for loop and an if statement. Two parts. Let's start with the for loop. For I in range length unsorted list -1. Okay, whatever this means, we will get to this in a second. So this just means repeat this many times. Whatever this is, whatever number that might be, repeat that many times. And we have an index I. So for the first iteration, I is 0, 1, 2, 3, and you should probably know that. Each iteration, we just check for something. We don't do anything, we just check. If unsorted list index is greater than unsorted list index I plus 1. So what does that mean? So let's go right here, actually. So I will just do some commenting, and this is not relevant for the code right here. This is just some notepad, so you can see what I mean by that. So let's assume we have a list of 4, 7, 2, 5, and so on and so forth. Okay. So the first thing that happens is unsorted. So for the first iteration, I is 0. Okay, unsorted list 0 is 4 right here, and unsorted list 0 plus 1, so unsorted list 1 is 7. So this just simply asks if 4 is greater than 7, which is not the case, but if it would be, then we have this task right here, this operation. And this is a very nice thing to do in Python. We have two tuples and they just switch places. And to give you an idea what this long line means, it's the same as saying x, variable x and variable y equals y and x. So we simply swap. If this one would be x, so this 4 and this is 7, then we have 7 and 4. So that simply means after this line, after line 15, this one for 7 now becomes 7, 4. Obviously, this is not what is actually happening because, well, 4 is not greater than 7, so we skip. But let's say we have a different list. We have a list of 5, 2, 6, and 4. Okay? Now we do that again. If index 0 of unsorted list, so 5, is greater than index 0 plus 1, so index 1 of unsorted list, so 2, well, yeah, that's true. Okay, what shall we do then? Then swap. So then make it not 5, 2, but 2, 5, 6, 4. Well, that is literally what is happening. It's very simple and straightforward. So we just swap those two things. And what do we do then? Well, we increment the value of changes made. Why do we do that? We will see in a second. But we did that for the first part, so let's repeat the for loop. This time I is 1, so what we do now is if unsorted list 1, so 5, is greater than unsorted list 1 plus 1, so 2, unsorted list of 2, which is 6, then do that again, swap these numbers and increment change by 1. But 5 is not greater than 6, so we don't do anything. Now I is not 0, not 1, but 2. So if unsorted list 2, so 6, is greater than 2 plus 1, so 3, in this case 4. So if 6, right here, is greater than 4, then swap. Well, 6 is greater than 4, so let's do that. So we now have 2, 5, 4, and 6. Great. And we increment changes, so now changes is 2. And do we repeat again? No, we don't. Why? Because range right here is, well, what is it? If we have a list of 4, so length of unsorted list is 4, minus 1 means 3, so we repeat 3 times. Why don't we use, why do we have minus 1 right here? And this is simple, because we always check 2 pairs. We first check the first 2, so 1 iteration, the next 2, 3 iteration, the next 2 iteration, then 3 iteration, and if we would check another time, we would run out of index, so, or index out of bound, because we would check index 3 and index 4, but 4 doesn't exist. So we always only check when we have an array or a list of 4, we only check 3 times. Now we are done with the for loop. What is happening next? Well, fairly simple. We check if changes made is 0. Well, why do we do that? Let's see, what is happening now? If changes made is 0, no, it's 2. But if it would be, we would say it is sorted. But as changes made is 2, we don't have a sorted array. We made 2 changes, but it's still not sorted. So what do we do again? While not is sorted, no, it's not sorted, we repeat the entire process. But we don't start with the initial list because we changed the initial list. The initial list is now that right here. So we start again. Let me copy this one. So this is the next iteration. We start with this list and we repeat 3 times. For the first time we check, is 2 greater than 5? No, it's not. So we don't make any changes. Is 5 greater than 4? Well, yeah, it is. So we swap those 2 and made 1 change. 2 is now it's now 2, 4, 5, and 6. Yeah, let me actually do that, so we kind of have a nice. That was that was great. Nicer looking. There we go. So we now made 1 change, okay? And we run this now a 3rd time, and we check. Okay, 5 is not greater than 6, so we are done. We are done with this for loop, and we now check again. Is changes made 0? No, it's 1. Okay, so repeat again. Changes made now is again 0. We repeat. We start with now this list, and this list is now that 2, 4, 5, 6. So we start with the first one. Is index 0 greater than index 1? No, it's not. Next one. Is index 1 greater than index 5? No, it's not. Okay, next one. Is index 2 greater than index 3? No, it's not. Okay. Oh, we are done. Did we make any changes? No, changes made is still 0 because we initialized to 0 and we didn't increment it, so it's still 0, which means we can now set is sorted to true, and we break out of the while loop, and now, as you can see, it actually indeed is, I hate that, is now a sorted list. So we can say the unsorted list is now sorted, and we can store it as a sorted list, and we return the sorted list. So very, very simple, very straightforward. And as you can see, we always have to do 1 iteration, even though we don't make any changes, just to see that this is not, that we don't have to make any changes anymore. And just to be sure here, this is not the only way you can implement a bubble sort. There are many different ways. It's more about the general idea, but you can definitely tell. Let me actually, while we do that, get back the camera. But you can see that it's the idea that you bubble it through. So you go from the first two indices to the next two, and always blop, switch or don't, or switch and don't. So we always bubble from, well, yeah, it's already mirrored, so that's kind of nice. You always bubble from the left up to the right end of the list and go again and go again, and you always change something if there is something to change, until there is nothing to change anymore, and then you are done with the sorting, and then you return. So as you can see, this sorting algorithm is kind of nice actually, because if you are lucky and the list is either already sorted, or you only have to swap two numbers, two integers. So let's say we have an array of, or a list of 1, 2, 4, 3, 5, 6, 7, 8. Only 4 and 3 are switched or swapped, so we have to only go through one time. So we now switch or swap 3 and 4, and we go through a second time. Well, it's now sorted, so we can return. So O would be 2. It's a constant in this, in this case. But if we have, you actually could calculate the maximum walkthroughs for the bubble sort. If it is completely randomized, it can take a couple of times till you really have the entire list sorted. So there are upsides to this algorithm. If you're lucky and the list isn't sorted that much, unsorted that much, it is quite fast, certainly. And if we take a look at our terminal right here, right there, so we can say Python 3 bubble sort, and again, list of 10. Okay, you can see there's a lot of things going on. So the 10, 8, and 7 all have to bubble all the way through to the end, and we have to take everything from like 2, 4, and 3 all the way to the left. So this will take, well, only 0.1 second, but again, this time doesn't really matter for this short arrays or this short length of lists. But you can see logically that this takes quite a couple of more iterations, and we actually can see that. Let me quickly do a counter. So we just say counter equals 0, and every time we went through the loop right here, let's just say counter plus equals 1, and after that, when we are done, we just say print counter. Okay, so we can see now how, it's just count. Let's just change it to counter. There we go. So we should now be able to see how many iterations it takes. And let's run that, if I didn't make a mistake. And 8. So it took us 8 loops. As you can see, it's right somewhere in between here. So, but this is the 8. And if we run this again, now it took us 9 iterations. Run this again. Now only 6. So you can see it changes. And if we would do this again and again, sorry, 9. So you can see it changes. And if we now go to, let's say, 1,000, blah, 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 and wow, you can see it took us already 3.2 seconds. And if we scroll up, it took us 955 iterations, which is quite a lot. And if we do this again, remember 955, and we run 1,000 again, bubble through, and let's see how long does that take. Okay, so but in this case we can see luckily very similar, 949, but it's slightly different. So this is like the real indicator how efficient this algorithm is, because you can actually see how many iterations it takes. And if we would be lucky, I could manually code that now, but I won't do this. But if we would be lucky, we could actually get a random list that is actually almost sorted, and we could get to like let's see, 938. So we could get to technically to something like 2, even though we only have 1,000 integers. If it happens to be that most of them are, you can see this is actually quite quick. So let's see, but this this case it took even longer. So you can see it's roughly always like 900 something, and this is just because the shuffle algorithm does a pretty good job in actually shuffling it. So this is kind of the what you could expect if you have a list of size 1000. You pretty much need almost 1000 iterations to actually sort it, which is technically O of n minus a couple of iterations. But it's, well, we can shorten this to saying, okay, it's O of n, or big O of n. So it's not really efficient, but if you would have a not so good algorithm of shuffling things, and it would actually shuffle things, or your list that you try to sort isn't that messed up, it's just pretty straightforward, there are just a few integers swapped, it would be quite fast actually. So yeah, I hope this was very useful and it was easy to understand. I try my best to phrase it as simple as possible, and again, if you are a more advanced programmer or developer or whatever, this algorithm, this function isn't focused on efficiency or elegancy or making it the most Pythonic. It's just making it the easiest to understand how it actually works. And yeah, next time we will take a look at the final of these three algorithms, the merge sort algorithm, which is yeah, a lot of fun, and I see you guys in the next one.